Tutorial 1, Part 4, Elemental Trends, Secondary Bondings, and Bonding Strength. Electronegativity and elemental trends. Electronegativity is the ability to attract the shared electrons towards itself. Generally, metals have a smaller ability of such ability than semi-metal than non-metals. And it is quite logical, because if you want to consider the bond nature of those kind of elements, you will have the same conclusion made here. Metals will form metallic bonds which they give up their electrons. Semi-metals are between metals and non-metals. Non-metals, they tend to accept electrons to form covalent bond or ionic bond. There are some factors which affect electronegativities. Distance between nucleus and valence electron, which is represented by the number of shells or the number of period or the principal quantum number. For higher distance or for larger distance, the electronegativity will be smaller, as the attraction force is smaller due to the distance is larger. The amount of positive nuclear charges will also affect the electronegativity. For higher amount of positive nuclear charges, they will have a higher electronegativity. For example, within the same period, in the elements at the righter position, they have a higher atomic number. That means they have a higher positive nuclear charges. By the definition of Coulombic laws, we know that for a higher amount of positive nuclear charges, the attractive force is higher. And by this way, we have concluded some electronegativity trends in this way. This one represents the first term or the first point. This one represents the second one. So in general, the trend is like this way. And however, for noble gas electrons, their electronegativity is usually undefined because we can't measure it, as they are chemically inert and we seldom form any kinds of chemical bonds with other atoms. And that's why we have no method or nearly no method to define the electronegativity for those noble gas elements. So due to the variations of electronegativity of elements, ability for attracting valence electrons will vary. Therefore, this accounts for the bonding natures between various elements. Consider two elements X and Y. If the electronegativity of X is much smaller than that of Y, the bonding nature will be ionic. For example, MgO. If the electronegativity of X is smaller than the electronegativity of Y, then it is polar covalent. For example, CO2 molecules. But if they are the same, their electronegativity is the same, then it is a non-polar covalent bond. In non-polar covalent bond, the electrons are shared equally in an equal distance. For polar covalent bond, the electrons are still shared, but the distance of electrons between each other atoms, they will be close to the atoms with a higher electronegativity. Therefore, no bonding, by this definition, is not 100% ionic. And for covalent bond, they can also have ionic natures. So there is no definite, no necessary to have a 100% covalent bonding nature, and there is no actual 100% ionic bonding in this world. It's a picture which explains the ideas I just mentioned. For non-polar ones, bonding electrons are shared equally. There is no partial charges on all atoms. Polar covalent, bonding electrons are shared unequally between two atoms, and there is partial charge of atoms. Ionic bond, it is a nearly complete transfer of one or more valence electrons, and there is a full charge on resulting ions. Using the ideas, therefore, we define ionic characteristics. Percentage of IC ionic characteristics is equal to e to the power negative delta x to the power 2 over 4 times 100%. If this one is more than 25%, we consider it as a covalent bond. If it is between 25 to 75%, we consider it as a partial ionic covalent bond. If it is larger than 75%, we consider it as an ionic bond. And here is a picture of percentage of ionic character versus electronegativity difference, which is this one, electronegativity difference. As you can see that for same type of atoms, they will form covalent bond, and therefore their ionic characteristics will be 0. It is pretty trivial. At the other side, for these atoms, they will have a nearly 100% ionic characters. But be careful, they are not fully 100%, but only nearly. At this region, they are polar covalent compounds. At here, NaCl, KCl, it is ionic bond, and they are compounds with ionic bonds. For regions here, HF and these few chemical species, they are partially ionic and partially covalent, their bonding nature. Secondary bondings. Secondary bondings consist of hydrogen bond, van der Waals force, and dispersion force. Dispersion force will exist in all molecules. Polar molecules, van der Waals force will also exist in polar molecules. For some polar molecules having high electronegativity atom, which usually F, O, and N. F stands for fluorine, O stands for oxygen, N stands for nitrogen, and there is a direct covalent bond between a hydrogen atom and this F.O.N atom. Then hydrogen bond can be formed. In their nature, and their natures are all covalent attraction. In terms of bond strength, primary bonding is much larger than secondary, and you can consider it at this way. Ionic bond will have a nearly same bond strength with covalent bond, but within covalent bond, polar covalent are higher than non-polar covalent, and ionic bond and covalent bond have a higher strength than metallic, and all primary bondings, ionic, covalent, and metallic, will be much higher in terms of the strength than those secondary bondings, which have such as H bond, hydrogen bond. Hydrogen bond is higher than van der Waals force in terms of the strength, and the van der Waals force is higher in terms of strength than dispersion forces. Examples of bondings and structures. Wipe the primary bondings of the following substance. The first one is HCl, hydrochloric acid. Second one is iron. Third one is the oxygen. The fourth one is the salt. For the first one, it is polar covalent because both of the atoms, hydrogen and the chlorine, are non-metal, and chlorine are very electronegativity or electronegative. For iron, it is metallic because iron itself is a metal. For the third one, it is non-polar covalent bond because it has only one species and it is non-metal. And oxygen will form a double bond with another oxygen atom. And in this way, the bonding itself will be non-polar in nature because they are same species. Ionic, for the last one, it is because sodium is a metal and chlorine is a non-metal, and there is a large difference in electronegativity due to one is metal and one is non-metal.